Thank you so much for the introduction, and thanks so much to you all for coming today. So I'm going to tell you a story about a government adopting a new technology. And so you might be excused for thinking, with everything going on in today's world, that with a teaser like that, I'm about to tell you about some authoritarian government using artificial intelligence for nefarious purposes. But happily, this is actually a story about a very open and collaborative project to improve public health. On January 4th of this year, 2019, the U.S. Centers for Disease Control and Prevention, or the CDC, which is the governmental public health agency in the U.S., they launched a new website that displays short-term forecasts of influenza activity in the U.S. The numbers displayed on this webpage are generated from the multi-institution collaborative ensemble that my team, this is an effort that my team has led over the last 3 years at the University of Massachusetts, Amherst. So what this means is that every Monday evening, we have a UMass Biostatistics graduate student collects the data from all of these teams who participate in this effort. She builds this ensemble model and sends our forecast to the CDC. And then on the following day, usually on Tuesday, the CDC updates their website and puts the data that we've sent them onto their website. So the CDC is currently using these infectious disease forecasts to improve their situational awareness of seasonal flu outbreaks and to communicate with both health officials and the general public. So this talk is sort of a high-level overview of how we got here with a U.S. governmental agency that's not usually known for being an early adopter of some new technology or some new fancy analytics, that them publicly standing behind these numbers and putting them on their website. So this is a story whose foundation is built on modern statistics and machine learning to some extent. But as the title of the talk suggests, it's really about a broader interdisciplinary effort that encompasses public health, risk communication, and data science. So before I get into the meat of talking about forecasting infectious diseases, I want to just sort of talk for a few minutes about what I see as sort of the role that forecasting is playing in society. I think it's playing an ever bigger and bigger role. So first of all, I think we can all sort of see how forecasts inform everyday decisions that we make. This is me on a typical morning, checking the weather app on my phone, looking to see, is it going to rain, what's the temperature going to be, and making a decision about, am I going to ride my bike to university, or am I going to take an umbrella, take the U-Bahn? And I do this every day, and I check my weather. I check the weather multiple times every day, and I'm using these forecasts to make everyday decisions. There are many other. I think weather is a sort of leading example of how forecasts are used, but there are many other examples, and here are just a couple that I picked out a little bit for their variety. So there are forecasts of solar energy generation that can be used by sort of residential or business for business uses. There are obviously election forecasts, which are done in the U.S. and have gotten quite a bit of press in the last few years, but there's also done in Germany and Australia and a handful of other places. There are earthquake forecasts as well, and these are just a smattering. There are also demographic forecasts and quite a number of others. So I often like to start with the sort of working definition that my group has been using for defining a forecast. I think it's important to think about this, especially as the term has become so popularized and you see people sort of referring to forecasts and talking about them. It's important to be fairly specific about what we're doing. So I'm going to read this to you, and then we're going to sort of unpack it piece by piece. So one way that we talk about a forecast is we say that it's a quantitative statement about the uncertainty surrounding an event, outcome, or trend that has not yet been observed, and the statement is conditional on data that has already been observed. So let's unpack this one piece at a time. As a statistician, when I think about a quantitative statement about uncertainty, I think about a probability distribution. And so here we're going to be talking about primarily focused on probabilistic forecasts, where you're assigning probabilities to all possible outcomes that could happen for this event that you're trying to predict. When we talk about an event, outcome, or trend that has not yet been observed, one way to sort of think about this generally is you're interested in some measured variable of interest. That's on the y-axis here, but more generally it could be a multidimensional variable. And you're interested in values of that variable that have not yet been observed. So, for example, this could be the number of cases of an infectious disease in some particular geographical area. It could be the spatial location of the eye of a hurricane, and you're interested in trying to project this forward. And what is this going to be in 6 hours, 12 hours, tomorrow, the day after, 1 week later, and so on. It could also be, more generally speaking, so you have these sort of projections of sort of the path of this variable, but you could also think about sort of summary statistics that are sort of summarizing this path. So for example, the maximum value observed within some period of time, or in the context of that eye of a hurricane that's moving, when and where is that eye going to cross a particular line in space? And for all forecasts are conditional on data that have been observed up to a given time. So in this picture, we're sort of saying here is this data that has been observed, and here we just have these sort of simple 4 data points in this toy picture. But of course, forecasts are made at a specific point in time. They may ingest just values from whatever time series you're trying to forecast, but they could more generally take in all kinds of data from all different data sources to make a forecast at a specific point in time. I'm going to talk just briefly about forecast evaluation. Of course, you could give whole courses on this, but I'm just going to talk briefly about the kinds of evaluation that we do in for our models. So we use a metric called a log score, which in just one slide, we can think of it as the log of the probability that your forecast model is assigning to the eventually observed outcome. So if the eventually observed outcome of interest is this Z star, that's that eventually observed 1 step ahead or 2 step ahead forecast, and your probability model, your probabilistic forecast is this F hat, and you look at the probability that F hat assigned to that outcome Z being the truth. You take the log of that, and that's your log score. So in general, higher scores are better, and you'll see later on that I'll talk about how we sort of aggregate these scores to come up with a sort of overall measure of performance. I want to just talk briefly about this. I like showing this picture as sort of, I think it gives a nice high-level overview. This is a picture showing weather forecast accuracy over time. So on the y-axis, you can see forecast accuracy, higher numbers are better here. On the x-axis, you can see time. This is covering about 3 decades of time, and it's showing the slow and steady increase in weather forecast accuracy across these 3 decades. So on the top, in blue, you can see 3-day ahead forecasts, 5-day ahead forecasts in red, 7-day in green, and 10-day in yellow. And so these slow and steady increase in accuracy over 3 decades is due in large part to sustained and really deep investment by governments all across the world in data collection infrastructure and research about how to forecast the weather better, and improvements in computational infrastructure that have happened. Obviously our computation has changed quite a bit since 1981, and at times going through this, these are all things that are contributing to these sustained increases in accuracy. From the perspective of infectious disease, we are very much at the early stages. Infectious disease forecasting is really, the first papers about this and the sort of sustained interest in it has really taken off just in the last 5 or 10 years. So, I like to think that we're sort of at the early part of this curve. We're a very young field compared to weather forecasting. There's a lot of room for growth and development, but this is a reassuring to look at a picture like this and say, we're not going to have these major changes overnight in accuracy, but that we are slowly going to see improvements over time. So let's talk a little bit now, turn to thinking about infectious diseases. I'm going to talk a little bit in general about forecasting infectious diseases, and then spend the most of the rest of the time talking about this one specific application for influenza in the US. So some of you may be familiar, and many of you may not be familiar with some of the very long history and very rich history of models of infectious disease. So this theory, some of the very foundational theory of models of infectious disease have been around for over 100 years. There's the sort of at the center of this is a model called the SIR model, which stands for the Susceptible Infectious Recovered model. This is an epidemiological model that has a compartmental structure and sort of simply talks about an individual entering a population. They're susceptible to some infectious disease. They become infected or infectious with that disease, and then they recover. And then maybe they can move back to being susceptible again, or maybe they never move back to being susceptible, depending on the disease that you're talking about. But at its heart, this is a mechanistic model of disease transmission. It's encoding a very specific biological understanding of disease transmission, how it works, and building from that mechanistic understanding. As sort of a historical footnote, there's a nice video up on YouTube from the 1950s showing an evening television program in the U.S. of a Johns Hopkins biostatistics professor, Lowell Reed, describing this SIR model on national television using math equations and using this sort of funny, sort of sticky blackboard thing. It's a funny little historical oddity. If you have any interest, it's worthwhile just spending 5 or 10 minutes and giving it a look, if nothing else, to see what this model looked like and what science looked like 70 years ago. So again, sort of staying in the big picture here just for another few minutes, I think you can sort of think of infectious diseases and infectious disease models as having these sort of two poles, one being these mechanistic models like this SIR model and all of the many variants that it can take on. And I would include in here maybe agent-based models, and sort of with modern computational infrastructure, we can build models that are simulating individual agents in a population and how they move and interact and make assumptions about their behavior. I think those are also sort of heavily mechanistic models built on assumptions about how the world works. There also are, on the other side, what I would call phenomenological models that are very much these sort of black box models. They don't care about what data generating process gave rise to the data that you're analyzing. They're going to analyze infectious disease case counts in the same way that they would sales of some product online. And from a time series sort of modeling, forecasting perspective, you might be able to get, this might be able to get you to a place that is not unreasonable and making good predictions to sort of completely ignore the infectious disease context. But in reality, most models in practice, whether they're forecasting models or models more designed for inference, they're operating in this sort of large, squishy middle center of sort of overlap of these two types of models that I call sort of a semi-mechanistic models. And so, for example, these might include sort of time series or regression-based approaches that include covariates that have a mechanistic relation to the disease of interest. Or maybe you have a spatial regression where you're taking into account, sort of the network structure and the sort of connectedness of a population. So it's a little bit of a marriage of these two different philosophies, and in practice, I think almost all models reside to some extent in this middle ground. This is a quote that's been attributed by one of my colleagues to the CDC director, who is said to have said, "We shouldn't just be historians of public health." And I think, obviously, while there's so much rich scientific knowledge that's been gained using all kinds of models for infectious disease and understanding understanding better how diseases are transmitted and what interventions could be effective, analyzing data retrospectively. I think this encapsulates nicely how the CDC is really turning their efforts, not entirely, but at least giving some credence to the idea that we can use forecasting models to help us better respond to emerging outbreaks and possibly emerging pandemics. This is a picture of Dan Jernigan, who's the director of the Influenza division at the CDC. And talking about some of the applications that he sees for forecasting. I'm going to highlight just a couple that I think are most relevant. you could imagine if you work at a hospital and you're in charge of staffing or ordering new supplies for the hospital, if you had a sense that there was a high chance that the flu season was going to peak a little bit earlier or a little bit later than usual, you could use that information to bring on staffing earlier so your staff isn't overwhelmed, or to bring in more supplies so that you're not going to run out of personal protective equipment right at the peak of flu season, which has come a little bit earlier this season. So those are some of the sort of institutional reasons, and there are a handful of others that are listed here. But there are a lot of challenges facing infectious disease forecasting, and I think really the leading one is data sparsity. So this is a picture of every dot on the left-hand side here is a weather station whose data contributed to building a large data on the climate in the world. And this is just a picture on the right of one of these weather stations sitting out in nature somewhere. And so over the last 50 years, there's been a sustained investment by governments to collect very detailed, real-time data streams, measuring, giving us very detailed meteorological measurements about all sorts of from all sorts of places, all over the world. There is no equivalent to this for infectious diseases. We rely on public health surveillance data, which is very good for what it is, and it measures important things. It's measuring people who are sick, but there's nowhere near the density and sort of direct measurements that we get and in real time that you see with weather. A second challenge these are sort of the two main challenges that I see for infectious disease forecasting. The second one is what some people refer to as a forecast feedback loop. So with weather forecasts, you can say what you want to about the weather. It's not going to change the weather. But if public health officials actually listen to our forecasts, it's possible that our forecasts could change the course of an outbreak. So on the left here, you can see these are workers in Thailand, public health workers in Thailand going around monitoring mosquito larvae in different places and looking at standing water. You can imagine if we were to say, hey, we think this district in Bangkok is at really high risk for a dengue outbreak in the next month. Dengue is a mosquito-borne viral infection, that you could send out public health workers to go do some spraying, maybe dump out standing water in places, and maybe that would have an effect. Similarly, after some dire predictions were put out about the Ebola outbreak in 2014 and 15, the U.S. and many other countries sent military troops and a lot of aid to West Africa, and perhaps that changed the course of the outbreak. These are things that are hard to measure right now, and of course introduce quite a bit more modeling uncertainty and modeling challenges for us. Here's a picture of some of these early predictions that incorporated some sort of different start times of interventions and their impact on the Ebola outbreak. So I'm going to turn now to talk about our forecasting seasonal influenza application in the US. This has been dubbed FluSight, and this is, the work I'm going to describe here is summarized in these two publications at the bottom, one that came out in PNAS earlier this year and another that is sitting on bioRxiv now, but we've just heard last week it's been accepted by PLOS Computational Biology. So the CDC has, over the last 6 years, run a forecasting challenge. It's sort of, it's not, they really don't like using the word competition because really there's a very nice collaborative and friendly network of people who are all doing this. They do rank models every year, so you do have a sense of which models are better, but it really is, I think it's true to its word, that it really is more of a challenge than a competition. And so the background of this is, here's the setup. So here's a map of the US. It's split up into 10 different regions. Each region is made up of a small grouping of states. They're sort of roughly geographically similar. So these are fairly large regions, all with quite large populations. And what the CDC monitors, one of the main indicators of of influenza activity that public health officials turn to during the flu season is this measure of influenza-like illness. So influenza-like illness is a syndromic classification. That means it's based purely on symptoms. You go to the doctor, and if you have a fever plus a cough or a sore throat or some other secondary symptom, you have ILI, regardless of whether or not you have laboratory-confirmed influenza. And this metric of ILI is the percentage of all doctor's office visits that are due, that are all outpatient doctor's office visits that are due to where the primary complaint is ILI or influenza-like illness. And they're looking, they weight, when you're looking at it at a region scale, they take a weighted measure, weighted by population. This is only an estimate because it's not, again, we don't have sensors everywhere saying this is exactly how many people are going to the doctor. We don't have an exact denominator. We don't have exact numerators. But these are samples from representative facilities, healthcare facilities in all these different regions. So you can see here on the bottom the time series of a selected few of these regions, and a few things I think stand out. One is it's very distinctly seasonal. Flu is very similar here in the US as it is in Germany, both being in the northern hemisphere. So there's sort of an off season in the summer and then a peak in the winter. A second observation is that there's quite a bit of region-to-region variability, and this is partially a figment of, I think it's more a figment of the reporting systems and who's reporting than it is of like actual differences between the regions. But nonetheless, they're fairly consistent, or they can be fairly consistent from year to year. But you can see that, the bottom, the sort of the troughs here of this seasonal activity can be often sort of 0 or 1%, but they can get as high as like 7, 8, 9, 10, 11% at the peak of the season. That's like 10% of all doctor's office visits are for something like flu. And the third thing is that the peaks, while the peaks are fairly consistent in the winter, there can be sort of from a public health perspective meaningful differences in when that peak intensity is happening. So sometimes it happens just before the new year, right around Christmas, and sometimes it happens several months later in mid-March or so. So with all of this in mind, the CDC, to their credit, has really done a huge amount of work thinking very carefully and quantitatively about what they want forecasts for. So they have said, here are, we want, as part of this flu site challenge, every week throughout the flu season, and that typically starts in late October, early November, and runs through May, they ask teams to give them probabilistic forecasts of these 7 specific targets that they say these are targets that have public health relevance. And so those targets are 1, 2, 3, and 4 week ahead forecasts of ILI in each of these regions. They ask for a measure of peak intensity, so when the season peaks, how high is that peak going to be? And then they ask for 2 targets that are defined on the time scale, so meaning that they're asking for a forecast that's telling us when the peak, which week the season will peak in, and which week the season will onset. And they define onset very specifically, saying here is a regional baseline that they define for each region separately. And they want to know what the first week is where this ILI measure is going to go above that threshold and stay above that threshold for at least 3 weeks. So these are the 7 targets that the CDC has says we are interested in seeing this information, and they are now conveying this every week to decision makers at the CDC and the general public. The last piece to note here, and this is again sort of tied to this data sparsity issue, is that there's a lag in data being reported. So that when we make our forecasts, a 1 week ahead forecast is actually for last week. And the 2 week ahead forecast is for this week. And this is just because it takes a long time for data to come from the Sentinel sites that are reporting how many patients come and who has ILI, getting that data to CDC, making sure it's clean, and releasing that in a sort of standardized public format by CDC. So there is this lag in reporting that means that in those first 2 weeks, our forecasts are what some people refer to as nowcasts, because they're just kind of catching us up to now. It also means that in these first 2 weeks, there's quite a bit more data that we can bring to bear in our forecast models, because there's data about the world that is not tied to these public health surveillance reports, and we can use that to help us make good predictions about what's happened in these 2 weeks. So the goal of this project that I'm going to be describing here was to try to bring ensemble models into infectious disease forecasting and show that these ensemble models both have good overall performance and that they have consistent accuracy every year. One of the things that you see with a lot of these individual component models is that one year they do quite well, another year they don't do very well, and the CDC has invested so much time and energy and political capital in having people sort of believe in and sort of trust these forecasts that they really can't risk having a model that one year is going to do really well and another year is not going to do well. And so an ensemble model is a natural choice because they're known for reducing variability in forecasts. And I think this feeling from the CDC is summarized nicely here by one of our other collaborators, Carrie Reed. She says a bad prediction is worse than no prediction at all. We want something that's going to be consistent year in and year out. So I've mentioned ensemble models briefly a couple times in passing, and just to sort of show you visually, and we'll get a little bit into the math of what we're doing, but if you have a bunch of probabilistic forecasts, and this is what we get, we sort of get a bunch of these from a bunch of different teams, and then we have a sort of model averaging technique that we do to combine them into a single forecast, a single cone of uncertainty. We've shown a picture like the above to Dan Jernigan at the CDC, and he said, "Oh, this is too much tangled spaghetti for me. I need one forecast." So it's nice and simple, and this is what we've tried to do. So I'm really up here as a representative of what we've called the flu site network, and this is a subset of teams that participate in the larger flu site challenge. It started out with 4 groups, and as you'll see later, now we have 8 groups. But these are 4 groups that have been participating from the very beginning. It's the Delphi group from Carnegie Mellon University, Jeff Shaman's lab from Columbia University in New York, my lab at UMass Amherst, and a research team from Los Alamos, which is a research institution that's sort of government funded. So again, the motivating question here is, since maybe the second or third year of the flu site challenge, the CDC has been putting together, they get all these models, and right now they're getting maybe 30 some models from 20 different teams, and they do a very reasonable thing, which is they take an equally weighted average of all those models. They say, here are all these models, we're going to average them all together. Some of these models don't do so great, and some models are quite good, but they just sort of mush them all together and take an average, and this model has done reasonably well year in and for the few years that they had done it. But our question was, can we improve on this by taking a subset of those models where we have detailed information on how these forecasts have done in past seasons and come up with a way to weight these models based on their past performance? And can we show that a method like this improves on this equal weighted average? So there's sort of a process slide here. This took a long time to organize these 4 groups in different parts of the U.S. And sort of come up with a way so that we could do this in a fairly systematic and sort of organized way. So we sort of initially had the idea for this in March of 2017. It took us a couple months to put together a set of guidelines of exactly, this is what you have to submit to participate in this, and trying to be fairly specific, and also trying to be fairly prescriptive about what analyses we were going to run. We wanted to be very careful to not to pre-specify analyses we were going to run, pre-specify model choices, so we wouldn't be accused of nor be guilty of refitting our models and going and seeking after the model that's going to do best. We ran some experiments in the fall of 2017, and then starting in early November through May of 2017 and 18, we were submitting weekly forecasts in real time. All of this, the entire history of this project is online on GitHub. It's open and public. All the forecasts are there. Our manuscripts are there. So you can go and sort of look at it and explore for yourself. So some more technical details, and then we'll get to some of more of the fun results. So basically, the guidelines for this, for participation, where we said any team who wants to participate, and we invited all participants in CDC. We made sort of a public announcement to try to recruit people to do this. We said you need to submit 7 seasons of forecast. So you have to sort of turn back the clock and pretend that your model has been forecasting for the last 7 seasons. And we have tools that are available, so you can go back and sort of query and see what data was available at a particular moment in time. And so teams needed to submit to us the full set of weekly forecast files for each of those 7 seasons. So that means we're looking at a little over 30 files per model per season, over 200 files total per model. This ended up being a bigger data management problem than we had sort of initially bargained for. So we ended up with 100 megabytes per model of data in this initial run. And I think now we have something like 30 million rows of data in this particular data representation that we're using right now. And everybody had to provide some metadata about their model so that we could be a little bit organized and go back and look and see what each model was doing. So in this first year, after this public call and sort of all this administrative organizing, we ended up with these 4 teams. One group submitted 9 models, and then we had one group that just submitted 1 model. We had 21 models overall. So it's important to remember, again, this is a subset of all of the participants in the CDC flu site challenge. These are just 4 groups. And in general, the groups were submitting variations of this on their own to CDC, but CDC discourages teams from submitting all of their models and encourages them to submit just sort of 1 or 2 well-chosen models to the actual competition. There's a variety of model types and data types that are used in these approaches. There are 2 groups that have more sort of mechanistic approaches. Here's one that has sort of a Bayesian SIR model, but it's a little bit, they sort of make a statistical adjustment to when there's a big discrepancy between the model output and what the data is saying. There's a group that does also sort of an SIR variations on it from Columbia. They incorporate some climate and and internet search data as well. And then there are 2 groups that do more sort of traditional statistical models like SARIMA models or kernel conditional density estimation. There are a handful of sort of variety of approaches. There could be more diversity, and we're starting to see some this year in particular. We have quite a wider variety. But this is where we were to start. So again, back to just a little bit of the details, and then we'll sort of get into some of the results. For each of these component models gives us a predictive distribution for some target z, conditional on whatever data is available at that time. We generally think of that as x, the time of year, recent incidents, other covariates that are floating out there. We end up with m. In this case, m was 21 predictive distributions, and each of these predictive distributions for a region and a target is giving us a specific distribution. So the forecasts are made every week. Here's sort of a picture of the spaghetti for one particular week in the northeast region of the US. One thing that the CDC has been very particular about from the outset, I think very appropriately so, is that they want model scores that they can interpret in a way that has some that they can sort of describe to people at the CDC who are not statisticians and don't have quantitative training. So what they've settled on is a measure of what they call forecast skill, which is essentially an exponentiated version of the log score. So this is sort of messy math, but you can pick through it pretty easily. Here's that log score right here in the middle. We're taking an arithmetic average of those log scores across whatever your choice of subsets of model, region, target, season, and week. So we have all these sort of sub indices, and you could take an average over whichever indices you're interested in, and then you exponentiate that. When you exponentiate that and you do out the exponents and the logs, you end up with a geometric mean of the probabilities that this model has assigned to the eventually observed outcome. So we can sort of, if you squint and you wave your hands, you can say, well, this is representative of a sort of measure of central tendency, of how much, on average, in a geometric way, on average, how much probability did this model assign to the eventually observed outcome. And the CDC likes that because you can sort of translate that into a fairly tangible meaning. So here are some of the results for all these 21 models. We are still not yet to the ensemble modeling. We'll get there in just a minute. So the numbers, so let's see, on the y-axis here, we have all of the models, sorted, the top, the most accurate, and the bottom, the least accurate. And on the x-axis, we have the 7 different targets. In each of the boxes, you can see a number, and that number is this forecast skill, this sort of geometric mean of the probability assigned to the eventually observed outcome. And the color represents the percentage change over or below, the percentage difference in the forecast score from that given model versus a baseline model. And our baseline model is a model that has a sort of probabilistic forecast that doesn't update over the course of the season. As it sees new data, it ignores it, and it always is predicting a historical average of what the ILI was in this region at this particular time. So that model is this Reich Lab KDE model. It's just a kernel density estimate. And so that row is right here. It's all white, and all the colors are relative to that row. So there's a lot to digest here. I'm just going to highlight a couple of the key points. One is that for this 1 and 2 week ahead ILI, quite a few of the models assign over 50% probability to the eventually observed outcome. It's pretty good. However, a seasonal average model also does not do that poorly here, and so those relative scores, there's not as much relative improvement over that baseline, but there's some. And I think the second thing to point out is that the scores for the seasonal targets, which are these 3 on the right, when season onset is going to occur, what the season peak was, and when the peak occurred, the scores here in general are a bit lower. You have to sort of toggle back and forth to see, but these scores tend to be a bit lower. But the relative improvement over our sort of naive seasonal average model is quite a bit higher. So you see there's almost sort of 2 times the probability, and our best models are assigning over twice the probability that, that this average model is doing. So armed with all of this data, now the question is, how do we combine these into a reasonable ensemble model? So we used a version of probabilistic model averaging. So here's those little component models that we were showing before, F of C. And we're just averaging them together into a probability, a sort of ensemble probability density function using a vector of weights pi c. And so these weights are between 0 and 1, and they sum to 1. So visually, you can see if you just had 3 models, and they each had, here are these 3 different predictive distributions, you could, if you have these 3 weights, 0.5, 0.2, and 0.3, you imagine each of these little bar graphs that are representing these probability distributions. You scale down each of those bars by this weight, and then you stack them on top of each other, and there you have it. That's your new updated ensemble prediction. So in practice, we estimate these weights, but we've tried a couple different techniques. But for the approaches that we're talking about here, we use a fairly simple EM algorithm. We've also tried some gradient tree boosting, and there are a couple other approaches that are in the mix as well. But at the moment, we're just doing a very simple thing that's trying to minimize the overall log score of this ensemble. So I mentioned before how we pre-specified the models we were going to choose. So in this fall, before we were first submitting, we said, all right, the governing principle here is that we want to start simple. We don't want to launch in with some really complicated model, because we know already that this really simple model that just assigns equal weights can be a pretty hard thing to beat. That's been the case in different infectious disease applications that people have done in the last few years. And of course, it's, I think, fairly well established in quite a lot of ensemble literature that just taking an equal weighted average can be a pretty reasonable place to start. So that's where we started. We said that's going to be one of our 5 choices, is this equal weighted average. And then we're slowly scaled up the complexity. Next, we said, let's take a model that estimates a single weight for each model across all regions and across all targets. And so that means in the parentheses here, you can see the total number of weights that that each of these models is estimating. So if we're just estimating one weight per model, you're estimating 20, and once you've gotten 20, the 21st is given to you for free. Then we moved and estimated what we called target type weights. So we split those targets and said maybe some models are going to be really good at predicting 1, 2, 3, 4 week ahead, and other models might be good at predicting these seasonal targets, the onset, peak week, peak percentage. And so let's say that let's let the weights vary by sort of having these two different sets. And then we said let's let the weights model by target, and so every target has its own set of weights. And then finally, let's let the weights vary by every target and region. So this is quite, getting quite detailed now because we have 10 regions plus the national level, so 11 regions in total, 7 targets, 21 models, ends up being quite a few weights. So again, here we have these forecasts being made every week. We're using this ensemble approach to turn them into this sort of single ensemble forecast. And here's how we did it in practice. We used a cross-validation technique because we needed to choose one of these models to submit to the CDC. So we ran a cross-validation experiment where we had these 7 seasons of sort of complete sets of forecasts from everybody. We would leave out one season at a time. So we started by leaving out that 2010-11 season, and then we used the remaining 6 seasons to fit all 5 of these ensemble models. And then we generated ensemble forecasts for that left out season. And we marched through one season at a time. So we ended up with a complete set of out of sample forecasts for each of these 5 ensemble models. Bless you. So these were the results from that at the end of that experiment. So now the models are on the x-axis. We've taken the average forecast skill shown on the y-axis here. Every colored dot represents one of the seasons, and the black X represents an average for that model. So they're sorted again from lowest skill to highest skill on the right, and the red models are the ensemble models that we created. So this, again, we sort of were going into this, we didn't really know what we were going to find. It was reassuring when we did this that all of our ensemble models were on the far right-hand side here, with the exception of that equal weight model, which was just a couple back in the pack. Also, as it turns out, this Delphi stat model is also an ensemble model. So ensemble models were pretty solidly at the top of the pile here. And if you zoom in a little bit, and so now I've changed the ordering of these. Now I'm showing you just the 5 ensemble models, that same y-axis here. I've ordered them from simplest to most complex. And I think the nice thing here is that you can see pretty clearly what I see as like a typical sort of cross-validation curve where there's sort of diminishing returns on increasing complexity. So, there's not that much difference in practice between these 4 models. They're all fairly similar. There's maybe a little bit of increasing variability, and on average a lower score over on the far right side. There's not much to distinguish all these 4, but nonetheless there was one that was slightly higher than the rest, and this was the model that we chose to submit to the CDC based on our pre-specified criteria. So this happened to be this target type weights model, which I'll show you right here, has the, as I said before, here are the 21 weights, or 21 models on the x-axis, and one set of weights in the top row for the 3 seasonal targets, and then another set of weights on the bottom row for the 4 week ahead targets. So you can see there was one model, this Delphi delta density model, getting over 40% of the weight here for the week ahead, another model getting 24%, and another model getting 19%, but otherwise fairly evenly spread with some lower percentages. The seasonal targets were a bit more evenly spread. There were, 6 or 7 models here that all have above 10%, so that was sort of a nice more even spread between them. there was this moment of terror when we were doing this in real time. We sort of spent all this time and effort and had taken a lot of these groups' time to sort of build this collaboratively. And when we were running these, we had no idea what we were going to see. There was a chance that 1 or 2 models or 3 models from one group were going to be all that was needed for this. But it was a real victory for our sort of collaborative science approach in this, that all 4 groups were represented in these top 4 models. So it was like a big sigh of relief on my part after spending all this time to organize this and convince people this was a good idea, that it actually sort of bore fruit in this way. Okay, so then we ran our cross-validation, which I've explained, and now we chose this one model, and now it's being validated in real time in 2017-18. So it has this sort of further, you could think of this as like a training phase for the cross-validation, and now a test phase in this real-time season. And we've subsequently had another season as well, which I think I have a few results for tucked away at the very end. So the bummer was that 2017-18 turned out to be a very tricky season to predict. It had dynamics that were unlike any of the past 15 flu seasons on record in the U.S. So here's a picture of all the past historical flu seasons are shown with the gray lines here in the background. And the 2017-18 season, this is just showing sort of cherry-picking one region here in the southeast of the U.S. Here's the 2017-18 curve. So you can see it's had a higher peak than any by a couple percentage points than any other ILI curve on record, including the 2009 H1N1 pandemic, which was a fairly significant outbreak in the U.S. And of course, this poses a big challenge for models that are relying on historical data to generate forecasts about the future. So nonetheless, our model still did quite well. I'm just showing sort of a couple overview slides of the performance. What this is showing is the training period average forecast skill in the bottom, where the color is representing the rank. So here we have our chosen target type weights model here. We had an average 41.41 forecast skill. We're showing the best model from each of the 4 teams in the cross-validation phase. And then we're showing an equal weighted average of all models that were submitted to the CDC. So this is not just the flu site network models, but all of these 30-some models. And so then this is for those 7 training years, and then this is for the 2017-18 real time. The one thing to notice is that all of the numbers in the top row here are quite a bit lower than the numbers in this bottom row, and that's because this was a harder year to forecast, or our accuracy was a bit lower. But the flu site network, the flu site network model was remained the top rank of all these models that we put forward. So that was, I think, a sign to us that there was again a nice victory for this collaborative approach. So just a few conclusions before I make a couple final observations. So the idea here is that we've used in this setting, we've shown that these forecast models can, if you combine them together and use this weighting of based on historical performance, they can provide consistent, measurable, but sometimes fairly modest improvements over some of these other approaches. One of the important things is that they showed a reduction in year-to-year variability of these different of performance of these different models. And the final thing is that there's still quite a bit of room for improvement. We want to expand the network more, bring in more models, get more data sources, have a wider variety of different model structures that are in here. So our first set of forecasts for the 2019-2020 season are due next Monday evening. So starting next week, you can load up the forecast yourself on this. We have a nice interactive visualization, which now that you've seen it can be a little foreign at first when you first come to it, but now that you've seen this talk, I think you could go and be able to navigate it fairly easily and sort of see our forecasts evolve in real time for this upcoming season. As I mentioned before, we have quite a few the group has grown, and so now we've added another 4 groups, including the Biocomplexity Institute at the University of Virginia, the MOBS Lab, and the Machine Intelligence Lab. It's a split between Northeastern and Harvard University in Massachusetts, the University of Arizona, and Protein Analytics, which is an independent consulting group. All right, so just a couple observations about sort of big picture, what I think the future of infectious disease forecasting is. So I think one piece is really trying to figure out what are the weather stations of infectious disease forecasting. How can we find better, faster, higher resolution data to help these models do better? And we've started some work on this. We've developed some collaborations with a couple groups, a couple companies that run rapid diagnostic tests for influenza and other diseases. And some preliminary results. We haven't incorporated any of these into forecasts yet, but some preliminary results are showing that there's quite a bit of good correlation between these numbers, and so we think that they should be able to help. We've also worked with a group called UpToDate. Some of you may be familiar with this. It's a service. It's like a clinical decision support service where clinicians, you could present with, you go to your doctor and they can search the up-to-date information about diagnoses or treatments. And so it's sort of like a more focused version of Google search, using Google search terms and people just Googling flu or Tamiflu or something and using that to predict flu outbreaks. This is a little bit more focused. It's a little bit more close to sort of patient-doctor interactions. A second theme is going to be trying to localize forecasts. Right now, we're talking about forecasting in these very large regions, and there's quite a bit of heterogeneity in these regions, right? It's not like every location in these large 5-state regions, some of which are probably bigger than Germany. It's not like they're all experiencing the same level of flu. And so how can we further localize these forecasts? The CDC already has been running state-level forecasts. But we're hoping to even be able to drill down with some of this finer scale data to city, county, zip code level. Sort of a pitch for some of the methodological work that we're working on. I'm going to be talking about this tomorrow a little bit in Karlsruhe. Is sort of thinking about updating ensemble weights in season. So there are a lot of good reasons to think about doing this. One is that it's a big lift to ask teams to submit this huge historical set of data about their models. In some cases, it's impossible to do that if they're using a data stream that's just come online in recent years. So how can we adapt some of this methodology to incorporate models that may not have a long history so that we can sort of incorporate that and change the weights as we move through a season? Similarly, in, say, a pandemic setting where people are trying to generate forecasts and understand what might happen in the future, a method like this might be useful because there's going to be no historical precedent, and all of these models are probably going to be fairly inaccurate when we're just starting out. But trying to learn in real time how these models are doing and weighting them appropriately could be really useful. So I'll leave you with this question, and that is sort of thinking we've talked a little bit about some of the decisions that sort of hospital administrators could make and so on, but could you think about ways that if you had this sort of infectious disease forecast on your phone or your iPad and you looked at it, would there be decisions that you might make differently? If you've heard all of a sudden that there's a big risk that flu is going to be really intense in the next couple of weeks, maybe you add hand sanitizer to your shopping list, or maybe if you have a sick parent or a sick kid, you say, we're not going to go to the Children's Museum and have my kid play on the big bouncy structure with all the other kids, or you tell your ailing parent not to go to the shopping mall and you go for them instead just to minimize exposure. Maybe you get your flu shots a few weeks earlier. These are some examples of some of the ways that you might be able to change your own behavior given some good information about how the flu season is evolving. So finally, there are a lot of acknowledgments to make. First and foremost, again, I'm up here as sort of a representative from this larger flu site network that's ever growing. It's an effort that I've led, but there's really a lot of people who have built this work and contributed to it. You can go to our GitHub repository and see the number of contributors is quite substantial. We've worked very closely with the CDC, and we've just recently gotten some new funding to be a center of excellence for flu forecasting for them. So we're really excited about that, and it sort of formalizes our partnership. But the two people in particular are Matt Biggerstaff and Michael Johansson, who we've worked very closely with there. Finally, the Alexander von Humboldt Foundation is sponsoring a year of research for me here in Germany. This has just begun, so I'm excited to be here, and the idea behind that is hopefully to start doing some of this work using public flu data in Germany. We also have funding in the US that supported all of this work over the last 3 years from a variety of sources, including NIGMS and particularly the MIDAS program, which is focused on modeling infectious diseases. a DARPA Young Faculty Award, and now recently the CDC grant. So thanks to Tilman for orchestrating this event. It's a pleasure to be here, and all the folks at HITS who have helped make this a smooth sailing technically. Thanks very much for your attention.